My name is Ray Lee. I'm currently a faculty member at the University of North Carolina at Chapel Hill. My primary role there is in the Department of Radiology as a neuroradiologist. That means I read MRIs and CT scans of people's brains, spines, and sort of neuro-related things. Want to congratulate you all at reaching where you are right now. It's amazing to me, since I can't imagine I've probably not even learned as much biology as all of you have learned at this point in time, and I've definitely forgotten most of it. But I'm going to talk about the intersection, I think, of biology and engineering, and hopefully it'll be mildly interesting and sort of tie sort of what you're learning and the sort of facts, if you will, and some of the diseases into how I approach things and sort of my career path. That's my understanding of what people are interested in. I realize with a virtual sort of panelist type setup, passing along messages, it'll be a little harder for me to catch, but please feel free to try to inject if you can, or we can save them for the end, whatever makes sense. So I'm going to talk about a little bit one aspect of my research first, and then I'm going to loop back and then talk about how I got to where I am currently at, if you will. And those of you who think that I don't have a spell check, Clarity is the name of my lab or the group that I work with. And it's me spending a lot of time trying to figure out something to explain sort of through an acronym is what I try to do. And so the real goal here is to try to see clarity through the novel imaging devices and things that we do. So let's get started. I left in my School of Medicine disclosures, just so you know that, just so you're aware that I may have some potential biases or whatever, but for this talk, it probably doesn't matter a whole lot. So we're going to talk more about physics first, and then you'll see me reconnect that with the biology. The modern X-ray tube was essentially invented by William David Coolidge. This X-ray tube, or basically any X-ray tube that hopefully none of you have to have an X-ray for, uses the same tube that was invented essentially in 1912. In the US, we performed over 200 million X-ray studies a year. We perform over 80 million CT studies, all of which also use the same X-ray tube or the same type of X-ray tube. And so essentially these have been unchanged for now over 100+ years. What happened was William David Coolidge was currently at that point in time at the GE Research Laboratory. And what he did was, the first thing he did in that laboratory was replace the filament within incandescent light bulbs with a ductile tungsten filament. And while you guys are starting to age out of the age of incandescent light bulbs, you know exactly where that's been and how much that's changed in the last 100 years. And it was only with the invention of really, I think, LED lighting more so than fluorescent lighting that we've started to replace and been required to replace our incandescent light bulbs with the highly more efficient LED light bulbs. Coolidge turned around and did this essentially for X-ray tubes in the following year. And instead of using ionizing air as the source of electrons for X-ray production, he also replaced it with these tungsten filaments. The problem is this led to two inherent limitations of modern X-ray tubes, is that they're very difficult to precisely control, and it's very difficult to place multiple X-ray sources close together. Well, you may not know why that matters. As you walk through this talk, hopefully we'll be able to see that. So this is his original patent in 1913. This is the modern X-ray tube. And while there's a lot more fancy parts and more maybe more labels here on this lower one, bottom line is the critical parts, the anode here, and then the cathode here, correspond to the cathode here and the anode here, all of which is essentially unchanged. So I was a graduate student back in 2003 at UNC Chapel Hill when Otto Zhou and Jiangping Liu happened to publish a new article. I was literally that morning, I have written down the exact date. I was reading Science Daily, which still exists as a blog. Back then, blogs were still relatively new, and I rather enjoyed reading that particular blog. And I'm reading along about this invention of a new X-ray source. And having had some background in medical imaging at that point in time, I thought that was the coolest thing since sliced bread. The last line of this blog actually literally says that it was invented at UNC Chapel Hill. Oh my goodness, I was surprised. So Otto and Jiangping I literally reached out to them that day and I told them, you don't know me from Adam, but I'm the only person left on this campus who's actually ever built an imaging system with x-rays from scratch, that uses x-rays from scratch. You know, can I work with you? Remember, I was a grad student at that point in time. So essentially what they did was take carbon nanotubes and apply this concept of field emission with cold cathodes. And I'll come back to why this is important. I was physically on that day, in that morning, sitting about right here. The building that I was physically in, the old MR research building, is now gone, but I was sitting right there. Okay, fast forward almost 20 years now, and we'll talk about what we've done in the last 20 years. So a conventional X-ray source produces X-rays by heating up a tungsten filament to over 1,000 degrees Celsius. Electrons come flying off of that filament, just like an incandescent light bulb. It heats up, and then we apply an acceleration voltage to strike a metal target, in which that then produces X-rays. This is how every modern X-ray tube, be it inside a CT scanner or if you're taking a radiograph or an X-ray of your wrist, that's exactly what they use. Carbon nanotube X-ray production, however, is very different. We take a field, what we call a forest or field of these carbon nanotubes, which are nanometers wide and can be up to microns in length, and we apply an electric field. The easiest way I can describe this is the shock that you might get for those of you who live further north during the wintertime, as you touch your finger to something metal, that jump of electrons, that's exactly field emission. And this idea that very sharp objects allowed field concentration, which allowed the electrons to come jumping off. So by applying a large voltage across these carbon nanotubes, we can generate electrons. Oh, where to go? And then hit a metal target and produce X-rays. I show it pulsing here because instead of heating the metal target here, all we do is apply a voltage, and we can then take advantage of digital electronics and this concept of, very simple electronic control. So two critical advantages then come from carbon nanotube-based X-ray sources. First, they're easy to control, and second, we can pack these things close together. What I didn't talk about was this blue thing, this focusing cup. Remember, the electrons from the tungsten filament go all directions, just like a light bulb, right? You want it to go all directions. Well, that's an advantage if you're a light bulb, but if you're trying to focus your electrons toward a target, that's a disadvantage, and therefore you have to spend extra energy and extra space to add a focusing cup to focus the electrons so they only go one direction. Okay, so what can we do with this? Well, back in 2004, we developed, or I helped build the first micro CT at that point in time. We call it Cyclops. This is 2.0, 1.0, used a slightly smaller detector. This is a mouse holder, where basically the mouse, there's a little respiration sensor, and this is the X-ray detector. This is our first X-ray source, our first carbon nanotube X-ray source. And this is basically a setup for performing mouse imaging, such that they were head up, tail down here, and then they would rotate here. We then reconstructed those images to create CT images, respiratory gated CT images. So the whole idea is that we can freeze the motion of the mouse's lungs. Obviously, during each respiratory cycle, we just capture an image at peak inspiration, and then move to a new position to capture a new image. This progressed on to the second version, or at this point in time, third or fourth version of our micro CT scanners, where we called this Charybdis. For those who know Greek and Roman mythology, you might know the whirly monster. This is our goniometer that moves our smaller X-ray tube and detector in a circular motion around the mouse. You can see actually the mouse is there on the mouse bed. And we then demonstrated the capturing of both cardiac and respiratory gated images, and this is back in 2009. To this day, only our most advanced clinical CT scanners are capable of capturing this motion, and none of the clinical CT scanners can capture mouse heart rates, as I'm sure you know, are very high, typically at a bare minimum 150 beats per minute, in contrast to the humans, where our CT scanners start to fail at around 85, 90 beats per minute for a heart rate. So this is back in 2009, so you can see this is quite a while ago. We proceeded, of course, it's great to be able to image mice, but we want to look at human disease. And so this concept of digital tomosynthesis, which was very popular before CTs were invented, was something that we were re-exploring at this point in time. So the idea of tomosynthesis is, instead of going all the way around the object, you do a limited angle. So here, maybe 15, 20 degrees, We acquire a couple of X-ray projections. Then we digitally reconstruct that by taking this information and figuring out where the image sort of information is coming from. We can digitally reconstruct and identify objects that should be overlapping, right? For example, this cloud and this star, if they are simply overlapping, you wouldn't be able to see them because they are covering up each other. But using digital tomosynthesis and reconstruction properties, we can bring out the fact that there's a star hiding in the clouds. So this idea that you can move an X-ray source in this sort of limited angle, acquire the X-ray projections, digitally reconstruct. The cool thing is that it's much lower radiation dose and it's lower cost than CT for generating these 3D images. The problem is that this physical motion of the X-ray source causes motion blur, and that's a problem. If you've ever turned on the radio and heard this concept of 3D mammography, that's exactly what this is, digital breast tomosynthesis, which they use a single source and they move in that angle. There's also a disadvantage of these systems being physically large, but we'll talk about that in a little bit. So of course, what you can then do is take this carbon nanotube X-ray technology and then create an X-ray source with here's 30 beams, replace the conventional X-ray source here, taking it off here, replace it with this 30 beam one, and now you have a stationary digital breast tomosynthesis imaging system. This work was funded by the our University Cancer Research Fund, and then from a the Carolina Cancer Nanotechnology grant. That was a big NIH grant. But anyways, I was responsible, of course, for the first human studies related to this, where we essentially compared women who had breast lesions and compared them imaging on this machine versus a more conventional breast tomosynthesis or mammography machine. Here's a system in our breast imaging center over in the hospital. Well, you can apply this concept to also chest tomosynthesis. Instead of doing the full spin around the patient, we can do a limited angle one, and we call this chest tomosynthesis. Here's a repurposed security tube. There's 30 beams inside this. Remember, most and all essentially conventional X-ray sources have maybe 1 or 2 beams at most, and they can't even be operated at the same time. You have to switch between them. The idea here is that using these 30 beams positioned across over this phantom, that we can get the multiple angles, then reconstruct these images. We've applied this idea to lung nodule screening for the sake of cystic fibrosis, for performing calcium scoring of the heart, and then also looking at both novel development of new techniques with these types of processes for both chest tomosynthesis itself, and then also for identifying lung nodules for procedural purposes. In the top right of all these are my colleagues and or mentees. This is Taylor, for example, who was a medical student when he worked with me and is now one of our radiology residents on these projects. I realize these names are meaningless, so I probably won't introduce all of them. Here's a sample set of images of a patient with cystic fibrosis. You can see the port, that's what that line is, where we inject medications, antibiotics on a regular basis. The cysts and the fibrosis, it's a little not trivial to see and explain, and sometimes only a radiologist can really appreciate these, but here are some of the cysts and the thickened airways that are associated with the disease. UNC happens to be one of the top cystic fibrosis centers in the world, and so I'm very fortunate to have number one, a ready group of patients, but also expertise as the importance of imaging and their workups and their patient care. Of course, we can also move to other body parts. This is our stationary, or I guess partially stationary, orthopedic tomosynthesis system, where we use a repurposed X-ray tube in 3 separate positions, therefore acquiring 7 beams in each position, which gives us 21 beams total over a 40-degree angle. And then this allows us to get pictures of the wrist for a scaphoid fracture. As all of you probably know, scaphoid fractures are one of the most common fractures. It's a fall-on outstretched hand. Basically, when you fall, a lot of that when you fall, the energy is transmitted to your scaphoid bone. The scaphoid bone has a blood supply that is only comes from one side. So if you break the bone, you actually you potentially ruin the blood supply for the distal component of the bone. And so therefore, we have to catch these scaphoid fractures. If anybody's had a scaphoid fracture, you'll know. Doesn't matter if the first X-ray was negative, you would sit with 4 weeks with a cast on, just to make sure that a radio occult fracture doesn't develop or wasn't present initially. I call it our easy bake oven, really just to give a sense of how easy and simplistic this is compared to a conventional conventional tomosynthesis unit, which is typically room sized. This hopefully will play. I don't know if the audio will transmit. This is a conventional clinical CT. Hopefully none of you have had to ever be near one. That sound is actually, this is an older unit, but that sound is actually the X-ray source and detector rotating around, just like in our mouse micro CT system. And I want to give you a feeling for how large this thing is and how sort of complex it can be, because you're rotating a gantry that literally weighs hundreds, if not 1,000 pounds, and you're rotating it quickly in this big circle. G forces do play a role, so it's very important. There's a limit to how fast we can run these things. Okay, why do I talk about this? Let's not redo that one. So the original CT was invented in 1971 with what we call a pencil beam. So we took a single beam, a single detector, moved it and shifted it. We quickly realized that if we had a bigger detector, then we can do the same idea from a single source covering a bigger area. Then we got to be able to rotate both the source, X-ray source, and detector for our third generation CT. Essentially, every single CT scanner that's out there uses this third generation technique. You can see this has been around since 1975. They did try to invent this fourth generation idea where the source rotated around a ring of ring of detectors, and this is called an electron beam CT, or one of the manifestations was an electron beam CT. But unfortunately, these were too expensive to keep around, and so therefore, actually, there's no functional. Well, there's no companies making these anymore. There might still be one or two functional ones out there, but they're very long in tooth at this point in time. So I like complex problems. So the question is, can we build a stationary CT using our carbon nanotube X-ray sources? Because by removing the rotating gantry, we would potentially simplify the function and then therefore increase the robustness of the system. Why? Well, the military, there's a bunch of CT scanners that were sitting in Afghanistan that were often unused because they, even though they were top of the line scanners, some dust or poor environmental conditions would cause these scanners to fail on a regular basis. And guess what? Trying to get some medical equipment company to fix a scanner in the middle of a war zone is not a trivial process. And so we were funded by the Department of Defense to build a stationary head CT. The interesting sort of technical problem is that the X-ray sources must be in the same location as the detector, and that's why nobody else is silly enough to even try to build one of these things. Of course, I like complex problems, and so this is actually our stationary head CT where there's no moving parts within the source and detector side of things. This is a bank of X-ray sources, a second bank, and a third bank of X-ray sources surrounding a ring of detectors. They're offset just slightly. We call it our red, green, and blue planes in order to have X-ray projections available from every sort of angle. Therefore, we do actually move the patient the same way we do in a head CT, in a conventional CT scanner. But there's no moving parts except for that, and actually we just use an off-the-shelf medical bed for this purpose. This is our initial assembled system in our physics laboratory space. Here it is. This is a little noisy. I apologize. Scanning an ACR phantom. This is a test phantom. The buzzing is actually because of the table moving and not inherent to the system. All the fans you hear are just cooling fans and things like that of the system. And there it goes, stop. So let's not do that again. And here's actually our stationary head CT deployed over in our ambulatory care center. I've been talking about starting clinical trials for the last 6 months, and my grad student this afternoon just informed me he fixed his final bug, knock on wood, that we were facing, and hopefully we'll be able to wrap this up, shield the system, and get started on that clinical trial very soon. Here's some initial phantom images. No neuroradiologist would never necessarily claim anything involvement with these images, but we're also developing machine learning and iterative reconstruction techniques to deal with the errors and the artifacts associated with this. However, our bone imaging is actually pretty solid at this point in time, so I'm very happy with that. This is the phantom that is imaged here. Obviously, it's anthropomorphic. Long list of people who are heavily involved in this side of the project. Otto and Jiangping, and then Christy Insko, and a bunch of our trainees. I have a couple other projects that I'll talk about in just a little bit, and excuse me for half a second as I close my door real quick. Unfortunately, I'm giving the talk from home, and so I guess it's time for my son's piano practice. Okay, and that's my son a few years ago. He did actually quite amusingly. He's like, "Why does anybody want to hear about you, Dad?" But we will get to that in a second. One of my trainees recently, actually, because so a photon counting CT, we're not going to go into the technology, but one of my first trainee was a physics student who I can claim I taught her all the biology she knows. She's now, I don't remember her exact title, but I think she's the assistant director of the FDA for this office in the vitro diagnostics and radiological health division. She actually commented and wrote an editorial related to the brand new photon counting CT that Siemens just had approved a couple weeks ago at this point in time. So it was nice to see one of my trainees move on and know that I taught her all the biology she knows since she was a physics undergrad. Okay, moving on. So it's my understanding that you all are interested in hearing about my path. And so I'm going to sort of go over how I got to where I am now, and hopefully give you some advice and sort of suggestions, and hopefully let you see that there's a light at the end of your tunnels one way or the other. Let's see. Okay, this is my fairly relatively long educational path. I can definitely claim I was a very slow learner. And I'll go through each phase of this relatively quickly, but I grew up in a suburb of Kansas called Overland Park. Most people don't know it. I went to MIT as my undergraduate for mechanical engineering, UCSD for my master's degree, and of course, University of North Carolina at Chapel Hill for my MD, PhD, and subsequent medical training. Like most of you, I was heavily involved in science fairs, science Olympiad, summer camps, of course, when I was a high school student. I swore up and down when you asked me about at the same time of your phase in life right now. I misspelled engineer there somehow, but that I wanted to be a robotics engineer. This was right in the early 90s, late 80s. Robotics and robots were just becoming sort of more commonplace, and I thought it was the coolest thing. Then I went to RSI 90 West, and due to experience, so initially I went to RSI thinking I was going to do neural networks, because that's what, they asked us what we were interested in. That's what I put down in my form. And neural networks back then were still, I can't say it's in its infancy, but definitely hasn't reached the level that it has now. And thankfully, more for my sake, it may have been too early, because I don't know that we had the computer power to do what we can do now. But I was told by the director, unfortunately, it turns out it was my roommate, was only interested in computer science. And since they only had one computer science position, they really wanted to offer that to him. And so, we have a lab of a cardiologist that you can work in. And would you be okay with that? Just getting to RSI was exciting enough, so of course I was okay. But inside I was a little disappointed that I couldn't pursue this dream of being or learning more about neural networks or whatever back then. And the robotic side of things wasn't an option, so that was okay. Well, it turns out the first day in my lab changed my life and my sort of viewpoint on life in general, and definitely my research. And it's actually because of experiences in that first day in lab, where a child passed away unexpectedly, not because of our research, but actually on the clinical side of things, that it made me realize the importance of the practice of medicine. And really how I view it, and I learned then, was by us tackling problems by turning fundamental disadvantages of an engineering system to your advantage. And so that's where I really began my path towards medical imaging, through by a somewhat silly and ridiculous and totally random change in research topics at RSI. When I went to MIT, so I knew I was going to become a mechanical engineer guaranteed. I felt mechanical engineering had the broadest exposure to both mechanical things and also electrical engineering, and so I knew I wanted to do that. So I went to MIT knowing that I wanted to become a mechanical engineer first. But I happened to work, after being rejected from the first lab I wanted to work in, my high school research happened to be in polymer chemistry. I thought I was a shoo-in for what turns out to be one of the most famous laboratories related to polymer chemistry. And ironically, since I was rejected from them, I wound up in a lab literally across the hallway from them. But it was also my first exposure to what I call medically trained engineers. MIT Harvard has an HST program that the engineer PhDs actually do 2 years of medical school. So imagine these engineers who not only do their engineering PhD, but have all the training, the first 2 years of training of a medical doctor, essentially learning all the physiology, biology, pathology associated with the practice of medicine, but not the quote unquote patient care side of things. They learn pharmacology, but not necessarily would be eventually responsible for giving those drugs. And this was incredibly fascinating to me, that people could really take this level of biology and merge it with the field of engineering. And so this laboratory performed what I call electrical imaging of heart function. And on a daily basis, my grad student was a guy named Tom, who's at Medtronic now. And I was just totally amazed every single time that we'd approach a medical problem, and he sort of explained the biology associated with it, and then connect it with the engineering that we're going to use to explore this. As one side soapbox and commentary, there was no biomedical engineering program or degree at MIT at that point in time, and I was very happy for it. It turns out, in my opinion, I really wanted to become a good engineer first and then worry about the medicine later, because especially with these model of these students, I knew they could become well trained in biology after their engineering degree. So I started considering medical school at the time. I explored a couple different programs, but I wound up at UCSD first in the Master's of Bioengineering. So very similar field to biomedical engineering, but with some subtle slight differences, sometimes considered a little more biological, a little more mechanistic than classic biomedical engineering. When I was at UC San Diego, I was really fortunate to be amongst the founders of the field of bioengineering. I didn't realize when I applied what giants I was able to be around. You guys all know what integrins are. I spent with one lecturer spent almost 4 weeks on integrins, and maybe it was a biochemistry lecture, and I was very confused why we spent that much time on what seemed to be esoteric at that point in time. Well, it turns out she and her team had discovered them, and essentially I was being introduced to materials that would be slowly percolating into the field of vascular biology. It was incredibly out there to be amongst a group of engineers with a passion for biology, or biologists with a passion for engineering, and seeing them merge these things very fluidly within the same laboratory, with potentially PIs from different sides of the fence, combining things together. My research there was on contrast-enhanced ultrasound imaging, and I learned there also that with my MD advisor, he was also a radiologist at that point in time, who happened to have a master's degree in engineering, and he had developed a new field of contrast-enhanced ultrasound imaging by simply applying very simple engineering concepts that all the major companies had missed, a simple idea that they had missed, and we actually had developed one of the newest approaches to contrast-enhanced ultrasound imaging back then. And it turns out my first day in lab there was actually our first set of images that we ever acquired. And so it was such an exciting time to sort of see this evolve. But I also soon learned that good ideas aren't everything in medicine. Long story short, I finished my master's degree, and very soon thereafter, the FDA put a black box warning on all ultrasound contrast agents, which essentially killed the field of contrast-enhanced ultrasound imaging. I was fortunate to have moved on to UNC at that point in time, but I watched a field that I had just participated a couple years of my life literally disappear overnight because of this black box warning. When I started at UNC, the best medical imaging laboratory at that point in time was in the field of nuclear medicine. This is either SPECT single photon emission computed tomography, or PET, positron emission tomography imaging. And so I joined that lab, and I was particularly excited. I, could see a future in sort of developing new PET-based and spec-based tools. But then it turns out, literally about 6 months later, the Department of Radiology, whom I was lightly connected to, was going to hire a new MR physicist. So there, I had always wanted to learn MR physics. In San Diego, my goal was actually to join an MR physics lab, but I sat in on one lab meeting and everything was so far above my head that I realized that maybe was not the right time. And so I had to jump ship from the original lab, and I had to go apologize to that nuclear medicine research director and say, hey, I'm sorry, but this opportunity is something I've always wanted to do. I'm going to have to jump ship and join this laboratory. It turns out before my PhD finished, the head of that laboratory wandered up to Johns Hopkins to continue things there. So arguably, I don't know if it was the right choice for me, but I got to learn my MR physics. During my third year of grad school, and as a part of that original lab, the nuclear medicine lab, I actually built a micro CT system with them. And it's during my third year of graduate school, focused on MR physics, that I actually, in 2003, when that paper was published about novel X-ray sources. So during my PhD years, while they were supposed to be focused on MR physics, all of a sudden I started developing what people call a hobby in X-ray based imaging. Again, sort of silly and stuff that I don't recommend, but that's exactly the path that led me to sort of where my major focus is now. The one thing I struggled in medical school was that they don't think like engineers, and guess what? I think like an engineer more than anything else. And I think medical school curriculums have evolved quite a bit since then. UNC had a very, very traditional curriculum up to that point in time. So it was an opportunity for me to sort of force myself to have to memorize and learn things. I enjoyed learning, but I didn't necessarily enjoy memorizing every single bug that didn't seem to have a relevance to anything I was doing or planned on doing in my future. Ironically, the best advice I received during graduate school was this from a gentleman who unfortunately passed away a couple years ago from Stanford, Sam Gambier, who's a world-famous, world-renowned nuclear medicine faculty member. He gave a talk at UNC when I was a grad student. He said, oh, just ask him for a faculty position, meaning when I finished graduate school that he suggests before I graduated medical school, but after I finished graduate school and received my PhD, that I should just ask for a faculty position. I thought it was the silliest thing anybody ever said to me when I heard it, but it turns out it was the best piece of advice. Because during my last 2 years of medical school, all of a sudden, having had the PhD in hand, and because I was contributing at that level in terms of research, for example, Laurel, the student I mentioned first, she was actually my mentee, and I was her primary advisor when I was still in medical school. So you can see how messy that can get very quickly, but it turns out that it worked very well for me. You'll probably forget this since all of you have a couple things to worry about more first, but that is literally the best piece of advice I've ever received. So I want to talk lightly about my other research, primarily because I think it reflects on how I use biology and the biology I learned in medical school and before that to integrate into my research. I like to choose what I call holy grail problems, or seemingly impossible but important questions. And now I don't necessarily recommend that everybody do this, but this is how I approach things. For example, I'm just going to give one example right now, and I'll show you pictures of another example. Ultrasound is horrible at imaging through bone. So why not figure out ways to do that? So it turns out one of my collaborators is very good at imaging through the bone using some novel techniques. Well, for me, instantly, I'm thinking about chasing the things that are encased in bone. And of course, as a neuroradiologist, the spinal cord and the brain are the two critical things that are encased in bone and very worth imaging, in my opinion. And it turns out that about a decade ago, so 10 years after the black box warning was placed, that the black box warning was lifted on ultrasound contrast agents, reviving that field. And having been in the first round of things, I was in a perfect position to contribute my knowledge and sort of clinical expertise now to the team, our team locally that's doing contrast enhanced ultrasound. So one of my other major research areas is using MRI to perform ventilation imaging. If you know anything about MRI, this is a stupid idea. This is like, in terms of things you could do, about the worst possible idea. And to make it even worse, I wanted to do dynamic imaging, meaning actually watch people breathe. If you know anything about MRI, you'll know they're very long scans, they're very noisy, and very uncomfortable to begin with. So choosing to do this seems about as silly as possible. Well, it turns out I have some spectacular collaborators who are mildly just as crazy as me, and we took a 0.4 second sequence, an image. So we create this image or a stack of images in 0.4 seconds, and applying denoising techniques developed by YAP, we can now actually generate this type of image with our MRI-based ventilation techniques. This uses fluorine-19 based compounds. This is a bit of a long story, but I'll spare you the rest of the chemistry and the physics, but this is the type of images we can get currently. And this is multiple phases of the respiratory cycle as we actually have subjects, our cystic fibrosis patients, inhale gas and exhale gas. So you can see as the gas concentrates, these are breaths while we're giving more and more gas to the subject. This is mixed with oxygen, so there's no chance of hypoxia. And you can see the types of images we can acquire while patients are breathing this gas and then breathing it out. So again, incredibly silly idea to pursue, but by choosing this, we've been able to do something relatively unique in the field of MR, and definitely for the sake of cystic fibrosis and other imaging, such as COVID. So another example is graft versus host disease. When a patient receives a bone marrow transplant from another person, the new immune system obviously sees the patient or the person who received it as a foreign body and then wants to remove it if possible. Obviously, you do your best to try to match those things, match the HLA types, et cetera, but that there's still a chance that the new immune system will cause graft versus host disease to attack the patient receiving the bone marrow transplant. This is an area where radiology essentially plays absolutely no role at all. Well, guess what? That then becomes interesting to me, and therefore we actually worked to develop imaging techniques to try to predict it. These are mouse models that I'm showing you here. This is a autograft bone marrow transplant, where basically you're seeing DNA replication through one of our imaging markers. Those are the kidneys that are very bright. That's the bladder. That's the colon. And you can see maybe a little gallbladder excretion. So nothing that would suggest a signal of graft versus host disease. This is a bone marrow transplant to a mouse with no T cells. Graft versus host disease is mediated by T cells. Therefore, you can see that this mouse should not develop graft versus host disease either. Our last mouse who's spinning here on the far right, this is bone marrow transplant with T cells also present, and with not native T cells, but transplanted T cells. And you can see that we've all of a sudden got a very different picture. There's a bunch of, these are lymph nodes that are lighting up in the mouse, and even the bowel signal just looks more diffuse and more angry, if you will, to use a non-radiological term, as compared to the other images. And so we've carried this on into humans, and the signal there is less clear, but we still think we're seeing a potential signal, again, for a disease that radiology or imaging plays absolutely no role. And now we have a potential technique to try to explore this and understand it, with the goal of obviously improving the lives of bone marrow transplant patients. My 2 cents and advice along your paths. First, I don't suggest that you jump all over the place and do every single imaging modality or sort of cover the field as broadly as you do, as I have done. But it's most important to do what you love, and be a darn good, fill in your own blank first. My research and the way I do things is very different than most, because I am constantly using my understanding of the medicine and the engineering and the imaging physics to figure out which pieces fit together. We have a couple other projects that I've given off to other faculty members, because I have unfortunately too many ideas rattling in my head to do them all. So it's better for me to get them out of my head into other people's hands. And for example, I have one George, who's actually roughly my age, who I've given a couple of these projects, and he's recently become funded on his own for these ideas. As you can tell in my life, yes, life will give you lots of lemons. Don't just make lemonade. Do whatever you want with them, and explore these ideas to really do something new and novel with it. I think that will be the most exciting if you sort of path forward. If you listen to any of the Nobel laureate and how they got to where they got, often it's because life gave them some form of lemon and they had to work around it. And it's through that process they did develop their new ideas and new concepts that for which they received the prize. I think it's important these days, and I have to stress this because often I see trainees who don't necessarily understand this. I happen to have incredibly good collaborators through partially a weed out process. I'm partially trying to be a good collaborator with myself. So you want to be a good colleague and mentor. We have to train the people behind us. They will help support you. And the same way you had mentors support you in the past and obviously in the future also. Research requires collaboration to be successful. My first funded research project as a faculty member was a collaboration and discussion that I literally started 15 years ago when I was bored and not bored in lab, but necessarily wanted to take a little time off and go think about other science other than my MR physics. I'd walk down the hallway to this computer science lab, and Stephen, who remains a collaborator to this day, and I would just shoot off random ideas and things that we thought would be cool if we really had the time. This is a full faculty member at the time, a junior faculty member, talking to a first or second year grad student, shooting the breeze. And we remain good friends and collaborators to this day, with us bouncing lots of crazy ideas off of each other. Our lab meetings and meetings are almost silly sometimes about how much we do and sort of the random ideas, but you can see they can lead to funding and hopefully new and novel things. Life is incredibly unpredictable. COVID, obviously, nobody, well, except for some epidemiologists and or people who knew viruses, I guess, could have predicted. But then the secondary effects and the need for particular areas of science. It's just amazing. I think that's what's popped out. So many of my own colleagues, including my own former RSI friends who are now world famous because of their predictive models that predicted COVID transmission in the early days. Then secondary to COVID, who would have ever predicted the contrast shortage that you're hearing about right now in the news, almost now on a daily basis, that I've been hearing about for the last 2 or 3 weeks? Well, our students right now are looking into, my students are looking into ways we can modify simple X-ray based systems in order to improve our conspicuity of contrast or use other things as a contrast agent. So again, highly unpredictable, but obviously with the right skill set and background, you have the potential to make a difference. Anyways, I will stop there, and there's my contact information, and obviously I'm happy to take any questions. I see one question: is there any relevant clinical purpose for the MR scans for ventilation? Absolutely. I really breezed over that, but the whole point is, obviously, if you want to determine lung function, there's 2 components, right? The first component is, does oxygen get to the portion of the lungs that you're interested in? And for cystic fibrosis patients, that's pretty important because the airways, as in, or even in asthma, as an example, if the airways shut down, then the gas, the ventilation gas may not get to the alveoli. And obviously then, therefore, even though they may be open, there may be air trapping and other things. And so our ability to measure ventilation this way helps us understand the ventilation process. This is especially true for cystic fibrosis patients because of the changes in their lungs that may lead to poor ventilation. But the interesting thing, and I didn't want to get too deeply into it, is that we can actually potentially, the second part of ventilation is obviously not just getting the oxygen to the lungs, but then getting the oxygen across essentially the endothelial cells, right, and oxygenating the blood. And so I'm postulating that using a technique with our fluorine-19 gas, or actually with 2 different techniques, that we can actually measure both local oxygenation with the gas. How cool is that, right? How do you measure oxygen anywhere you want to in the body? It turns out it's actually very hard. So we can use fluorine-19 ideas for that purpose. That's beyond what you want to learn about in the chemistry. But the other cool part is that we can also measure gas exchange and the extraction of oxygen from our ventilation gas into the bloodstream, because obviously that's important. If you have, so that's what people are suspecting, that long COVID as evidenced in the lungs is because of thickening of the airways or thickening of the endothelial cell layers so that we don't have good gas transport either. So these are all critical, obviously, in understanding lung diseases. Other questions?
1 second. Wait.
Or I think it's like,
Do you want to speak in here? It's not yet.
oh, I'm sorry.
Yeah, there's a question. Can you hear the voice?
Just barely. Yours is more clear.
Hi. Oh, okay, I just want to say thank you so much for coming to talk to us today. So I feel like a lot of the things you said resonated with me because like I also went to RSI and it left me in a similar like position in that while you're interested in applying like engineering to biology, I'm interested in applying like CS to bio. And now that there's like more specialized majors like computational biology or like biomedical engineering, do you feel that it's like if you're interested in like an interdisciplinary field, do you think it's better or like maybe
Nobody will.
like, do you think like would you rather like major in a broad field, like for example applied math, or something more narrow like computational biology?
Well, my perspective is this, and this is specific for medical imaging and my sort of relatively narrow field. My collaborators in computer science are real, quote unquote, real computer scientists. They aren't radiologists or whatever that have retrained as a computer scientist, right? I work with a couple people who are literally tops in their fields on this, and they are computer scientists with an interest in medical imaging, not somebody who's gone the other way around. So the BME example is the best example, and this is what I tell everybody, to the consternation of most people, and especially undergraduate BME programs. A typical undergraduate BME program has introduction to biology, introduction to mechanical engineering, introduction to electrical engineering, et cetera, et cetera, et cetera, introduction to material science, introduction to vascular biology. So you have an introduction to everything. The problem is, what do you need in graduate school? You need an expertise in one of those areas. I want to, if I'm going to hire you as a student, I want to see somebody who has a depth in physics and engineering, mechanical engineering, programming, something, and who understands that they can apply those advanced techniques to a biological problem. So my opinion, personal opinion, especially for BME and things like that, is that be a darn good engineer first, right? Be the extreme expert in algorithms related to the things that you're interested in. And you can learn, ironically, I realize I'm talking to the USA Bio group, but then you can apply that to biology or medicine or whatever. And, Laurel is a spectacular example of that. She was a great physics student who did her job. I taught her literally all the biology knows. It's a running joke between us. And she is now at the FDA. Right, she knows more than she learned a lot on her own. Don't get me wrong, I'm not taking all her credit there, but bottom line is she can learn that side of things, right? So if you're interested in computational biology, for example, my gentle suggestion really is be the best darn computer scientist, I think. Now, is it math versus computer science? That I think is a little more complex, and it's hard for me to point at. And as we super specialize, you can be a darn good computer scientist in a computational biology lab, and I think ultimately you'll do better. You'll do better because presumably you'll also want to lead with ideas, and that's the collaboration part, right? It's because you can see algorithms past this field. If this is computational biology and you grew up a little bit over here, you can see how those fields intersect and apply those principles. And that's why it's so much fun for me to work with these computer scientists, is they're drawing things from machine vision, they're staying up to date in other worlds, not just my tiny little world of medical imaging. And it turns out, as an example, medical imaging AI projects are typically 1.5 to 2 years behind the rest of AI. So why not work with the leaders and the rest of AI? Because I know what I need in medical imaging, and therefore I can work at a different level.
Thank you so much.
There's a question in the chat, in the Q&A.
I see the scans, the clinical purposes for the MR scans. I tried to answer that previously. If I didn't, let me know. Is there another one? Oh, wait, there's another one. Sorry.
Peter.
Let's see. Peter, very good questions. So this is the part that you don't want to be me. My head bounces between these projects in the most ridiculous manner, and it's a horrible idea. I am 20% clinical, so I read films typically 1.5 days a week at most, and 80% research. It's maintaining that balance is difficult because I compete against for NIH grants against the people who are 100% research. But I love reading films also. That one day a week sort of reminds me of the reason I'm doing these things. I'll go from a stroke patient to a tumor patient to a patient with a headache to horrible trauma to other horrible diseases, right? You don't want to get your brain scanned because usually that means something bad is going on. So that's how I sort of divide my time. These projects, it's a function, I'm probably 50% in the X-ray world, 25% in the MRI world, and then all the other projects fill in my other time. And typically at this point in time, I have heavy collaborations that help me support this. We have a team of 2 to 3 faculty, other physics faculty that focus on the carbon nanotube world side of things. And so a lot of it's, for me, working with them to build these physical devices. While I know enough of the engineering these days, it's not like I deal with the high voltage electronics myself and things like that. I've got a couple of students who handle that. The black box agent thing was particularly interesting for me because I actually had just left UC San Diego when it happened. So it was sort of a sigh of relief that I wasn't there, but also sort of also recognizing as a person who's worked in that field that something wasn't right. And it took the industry with money, and this is the part of things that is difficult to explain, right? Because, we know money drives a lot of it, but you could have the most interesting, perfect contrast agent, but if somebody's not willing to fund you to commercialize it, it'll never get used. And that's something I think us researchers take a long time to understand. And ironically, the carbon nanotube group has understood very well because one of them grew out of Bell Labs, the group that you guys know invented the transistor, et cetera, et cetera. And he was very comfortable with that commercialization side. They've spun off 4 or 5 companies. If I were in my office, you'd see my wall behind me covered in patents because of my work with them, basically generating new ideas for imaging devices and things like that. And unfortunately, that's the money that's required to convert these things from a research practice or something in the lab into clinical use, right? Is the money to fund that. Thankfully, they're very good at it, so I don't have to think about it. And our first product was a dental product, primarily because dentists make a lot of money off of x-raying your teeth. And so that was the first logical commercial product. I also told them that's not something I'm particularly interested in. I don't feel like we should be irradiating the teeth more, so I'm not a part of that project as much. Other questions?
Bella, there's a question.
Should I?
Yeah, why don't you come up here and kind of shout a little bit?
Should I just shout at the microphone?
Yeah, I can almost hear you.
I know you said asking for a faculty position was the best advice you'd ever gotten.
Uh-huh.
Do you have advice for setting a balance between advocating for your own needs and not coming across as inconsiderate or arrogant? Often I feel like I don't want to come across as rude, but sometimes my needs get trampled in the process.
Presumably, sorry, I'm guessing all of you are in high school.
Yeah.
I think it's more difficult. I was spoiled. That's the only way I can put it. As a high school student, in terms of working with faculty. This is back before everybody, research now, RSI, this idea of having mentors for high school students was obviously relatively new back then. Not completely, not that uncommon, but there is still relatively few and far in between. While now it's become fairly standard. And I was very fortunate to have mentors who truly saw me as a mentee in terms of my growth. I didn't talk about it, but my first real job was at Caltech in a lab from a guy from Sunny Chan who discovered cytochrome, who's the world famous cytochrome CX oxidase expert. Why he gave me that job to this day, I will not understand. You're advocating, you need to speak up for yourself and ask, I think, and it's a balance. You're absolutely right, it's a balance. I have students that sometimes I think are reaching beyond that. We do our best to support them no matter what. And in truth, the worst they can say is no. And in fact, that's the advice. So my Kansas City mentor told me to go to Dr. Chan and ask for a job. That's literally what he did. I said, you are insane. You know how your parents push you to go to talk to a stranger and you can see the 5-year-old, right? panicking inside. How do I talk to this guy? I don't want to talk to this guy. I can't talk to this guy. So that's exactly how I felt as Dr. Helmuth was literally pushing me to speak to Dr. Chan and say, ask for a job. So I went to Dr. Chan, Caltech professor, this, cytochrome C oxidase expert, world famous, came out of retirement twice, once for the SARS, the original SARS virus, the second time for COVID, and said, hey, will you give me a job? Let's see. I emailed him 6 weeks later. This is toward the end of summer or whatever, toward the end of the school year. And I emailed him 6 weeks later, said, hey, do you remember me, the high school student that asked you for a job? A week later, I was at Caltech. I don't know why to this day. He actually phoned my mother, said, don't worry, I will take care of your son. And that's literally how I got my first real job, my first paycheck. It paid me $230 something for, for spending a couple weeks essentially as a lab rat at Caltech. But growing up in Kansas, that was something different. So advocate for yourself. Do your best. You should know, at least when you sort of come across as becoming rude, and for the most part, I don't think it'll be that way. In your laboratory, if you need something, either tools, supplies, I think it's perfectly fine to ask for that. Asking to be a part of publications, which you haven't contributed to, obviously that's a problem. But I think that's important. But I think it's also, you have such a long path in front of you. All of us want to get that first paper. My first publication was in a Portugal newspaper. It was a photo I took. Had nothing to do with anything science, except for it was the Ig Nobel, and I literally got paid, I think, $50 for that photo. That was my first publication. I was hoping it was some important science journal, but guess what? That was my first publication. So I think you'll need to find that balance, but feel free to speak up, because the worst thing I think they could do is say no. I hope that helps.
Thank you so much. That was really helpful.
MD, PhD. This is a fascinating part, I think. I know people who've gone all the different routes, but let me put it this way. Once you get into, as all of you know, so it's a standard MD, PhD program is 2 years of medical school, typically 4 years of PhD, then 2 years of the last 2 years, the clinical years of medical school, followed by then entering the internship, residency, fellowship cycle. Okay, so 2 med school, PhD, 2 then internship, residency, fellowship. Once you start back at that 3rd year or so of medical school, that path for you is essentially laid out until you get a research year in residency. Okay, so think about that. In that time, the likelihood of you doing research at any level is very low. I don't care how incredibly smart, time management, whatever, real life happens and starts really to trickle in that portion of your life. My son was born during that time of my life, during the residency time, things like that. So unless you're in a perfect environment, which I was fortunate to be able to, your ability to do research, especially semi-independently, is very low. And guess what? The field is marching forward their direction while you are in your medical training. Your PhD side of things is progressing a different direction. So my suggestion is really to try to get this stuff done as soon as possible. For the most part, try to get your training done as much as possible, because you have the training, you'll have the techniques. And once you get more solidly on that path, meaning sort of during residency or immediately post-residency, then that'll be the opportunity that you can start writing grants for yourself and being independent. Hopefully during that time, you'll have some basal level of mentorship and research that you can keep your skills reasonably intact. But as an MD, it's very unlikely you should be spending a lot of time, pipetting or doing mouse studies the way I used to, right? So I think that's why it's important to get into that phase of training as quickly as possible. Of course, I am the worst example of that, having taken this ridiculous meandering route to get me to that point. But that's the advice that I give to everybody, because you're not, anytime you do medicine, and the practice of medicine is going to take away from your research time, for good or bad. And depending on which career path you choose, then you're going to be at a disadvantage. And you might as well get your training stuff done as soon as possible, so you'll be in the best position later on. That's somewhat of an oversimplification, but it depends on how you want to balance your life later on.
Thank you.
Yeah.
Yeah, take care.